Howdy, eggs. So I like to create this additional video showing the parts cart that I would have shown in class, mostly because this gives me a chance to go a little bit more deeper into detail than what I might have been able to do in class, and also gives folks that didn't get a chance to see some of these things up close and personal a chance to do it as best as we can through the video. So the parts cart has lots of parts on it. It has a cylinder liner, a piston, connecting rod. I'll go through all of that here in just a moment. But what I wanted to first talk about was the engine that you see here. And as I probably mentioned in class, this engine has been modified by a student who, as an independent study, took an old diesel engine that we had in the lab. We didn't have use for it for measurement or testing purposes anymore, but given that it was a single cylinder engine, it makes for a great classroom demonstration about how an internal combustion engine works. And so the student took the engine and cut into the metal on the cylinder side here. So you can see where the student basically cut away at this side of the cylinder and cut into this portion as well to be able to expose the piston inside the cylinder. And then you can also see some of the internal workings. These are the push rods for the exhaust valve, and then the intake valve is on the other side here. You can see it just to the right of the exhaust push rod. I'll describe all of that more in just a moment. But the student cut all this away so that you could see the inside, and then he built this little plexiglass cover. We have to provide some structural support for the piston here, with it missing almost a quarter of the cylinder. If you didn't have that plexiglass guard there, the piston would fall out when being reciprocated back and forth, and then you wouldn't get to enjoy the demonstration quite as much because you'd always have to constantly be fixing the piston in place. As it is, you probably can't see it all that well in the video, but the piston rings had to be removed because the piston rings were, again, because they're not being held in place by a cylinder all around the piston rings would get hung up as they go below that lower edge there. And so just to make it easy for demonstration purposes, we removed the piston rings. And you can see that there's a little bit of rubbing between that plexiglass cover and the side of the piston there. That's not normal. I mean, you wouldn't expect or want to have that happen inside an actual operating engine. But again, for classroom demonstration purposes, it works just fine. And then, of course, this bottom portion here, there's a cover that has been removed, and it might not be obvious, but there's certain parts that are in the block of the engine that are structurally held in place by this cover that's been removed. And so one of those supports is actually supporting the camshaft. And in a moment, when I'm actually rotating the engine and walking you through the cycle itself, you'll probably see me hold my hand or my thumb here to keep this camshaft in place. If I don't do that, when I'm rotating the engine, the camshaft will have a tendency to come out from its proper location, and then it doesn't allow the push rods to follow the cam anymore, and then the valves don't work the way that they're supposed to. So I'll usually hold my hand here just to keep that in place. And of course, this handle, the handle obviously was also added by the student. And it's connected directly to the crankshaft. So this is the crankshaft that you see here. You can see there's a counterweight there on the other side. And then the big end of the connecting rod, you can see, is connected to the other side of the crankshaft there, right? And so that's what's causing the piston to reciprocate back and forth, up and down inside the cylinder. So that's the block, and that's the cylinder. Couple of other things that I'll point out before we start to focus on the head, and that is the fuel injector pump, or the fuel pump. This is the fuel pump that you see here, and then this tube that you see running from the fuel pump up to the fuel injector in the head is so the fuel pump is driven by the cam. The pressurization or the pressure actuation in the fuel pump is caused by the cam basically interfacing with a plunger inside this pump that pressurizes the fuel. So this tube is filled with pressurized fuel, and then at the time when fuel is meant to be injected, this plunger pump will give a plunge and basically momentarily pressurize the fuel in this line high enough that it can cause the needle inside the injector to open, and then fuel gets injected directly into the cylinder. One thing I'll point out real quick is if I position the piston just right and I hold my camera here and we don't get too much of a reflection, you can see the piston has a bit of a geometry, or it looks like a hole that is machined into the crown of the piston. We call that a piston bowl. That's actually where the fuel is injected, and that's generally where combustion takes place inside inside the cylinder of a diesel engine. And so that's where the fuel basically gets injected. So turning our attention to the cylinder head itself, so this side of the engine is the exhaust side. So this would be the exhaust port, and correspondingly, this is the exhaust valve here. And then on the other side, of course, we have the intake valve, and then we have the intake port located right here, okay? And then there's other things on the engine. For example, you've got a starter gear on the flywheel down there, and then this is some fins that are built into the flywheel as well to help with forced air induction to help cool the engine. Again, as I may have mentioned, this engine is air cooled, so it's got lots of fins designed in just about every place where you can put a cooling fin and allow that forced air induction from this built-in fan into the flywheel of the engine to circulate air all throughout the cylinder block and the cylinder head to keep it at a reasonable temperature. Okay, so what I'll do now is I'm gonna set my camera up so that I can basically show you the reciprocating action of the piston inside the cylinder, and then you'll also get a chance to see the valves actuate where, depending on where we start the cycle, I'll try to start it such that we're at top dead center of intake of the new cycle. So then you'll see the intake valve depress as we move the piston from top dead center to bottom dead center, and then the intake valve will close. Piston will move from bottom dead center back to top dead center during compression. Around that time, and of course you won't see this because there's no fuel in the engine and I'm not rotating it fast enough to build pressure to inject the fuel, but when the piston is at top dead center at that point, fuel would then inject from the injector into the bowl of the piston. You'd have combustion that would push the piston back down during expansion, and then you would begin to see the exhaust valve open, piston move from bottom dead center to top dead center, pushing the products of combustion out during with the exhaust valve open. Okay, so let's go ahead and walk through that, and then I'll point out some other fine-tuned details about this engine that you might find interesting. Okay, so we have the piston. You can see the piston is at top dead center right now. As I kind of rotate my handle back and forth, you can see that the piston is moving off of top dead center in either direction. And we're at top dead center at the end of the last cycle, so the start of a new cycle. And so as I rotate the piston from top dead center to bottom dead center, what you'll notice is that the intake rocker, and it's a little bit hard to see, I apologize. You're going to be looking at the rocker that's in the back here. This is your intake rocker. You'll notice that that rocker is going to, the push rod will push up based on the cam action. That'll push the rocker arm down and cause the intake valve to begin to open. And so I'll slowly work through this, and you'll see the piston moving down and the intake valve open. The intake valve will open or stay open until the piston reaches about close to bottom dead center. And then you'll see, actually even before we reach bottom dead center, you'll see the intake valve begin to close. Okay, so here we go. As I rotate, we're moving from top dead center to bottom dead center. You can see the intake valve is opening. Now the intake valve is basically fully open as I go mid-stroke. And now as I approach bottom dead center, you can begin to see the intake valve is closing. and the intake valve is basically fully closed about right at that point there. And that also corresponds to almost exactly piston bottom dead center, okay? So now the piston's at bottom dead center. I continue to rotate in the same direction. The intake valve is closed. Piston is now moving back toward top dead center during the compression stroke. And now again, we reach top dead center at this point. And this is when the fuel injector, so the fuel pump would be actuated by the cam to create a momentary rise in pressure in the fuel line that would squirt fuel through the fuel injector into the bowl of the piston, which of course we can't see because the piston comes up so high, it's being covered up by this metal. So fuel is now injected, combustion begins. You then have that combustion pushing the piston back down during the expansion stroke, and then we're nearing the end of expansion. We're nearing bottom dead center, and now you'll begin to see the exhaust valve. As I approach bottom dead center, you'll begin to see the exhaust valve open, the push rod for the exhaust valve, open the exhaust valve, and then we'll switch directions. And so we're at bottom dead center. We keep going. You can see the exhaust valve is starting to open. We keep moving up. The exhaust valve is basically fully open at this point. And now you'll notice that again, around mid-stroke, you begin to see that exhaust valve begin to close, so that now once we get to top dead center, now the exhaust valve is fully closed. And if I keep going, now the intake valve is going to start to open, right? You can see the intake valve beginning to open, okay? So that's the 4 strokes of the typical IC engine mechanical cycle. Now, a few kind of nuanced things to point out. The first thing that we can point out is that you'll notice, so if I go back into the previous cycle and then forward into the next cycle, right? I'm just going to do that action back and forth so that you can watch the piston and watch the valves at the same time. What you'll notice is that there's hardly any overlap between the exhaust valve. Remember that overlap means that the exhaust valve and the intake valve are open at the same time, right? But basically at this point right here, my exhaust valve is closed and my intake valve is closed. And my intake valve doesn't really start to open until my piston starts to move quite a bit away from top dead center, okay? So the engine has very, very little overlap. The other thing you'll note is that the intake valve closes pretty much right at piston bottom dead center, right? So I'm just going to kind of rotate around bottom dead center back and forth a bit, right? If you train your eyes on the piston and if you can see that rocker arm motion on the intake valve, right? When that piston is at bottom dead center, that valve is pretty much closed, right? So the exhaust valve closure happens pretty much right close to piston bottom dead center, right? There's not a delayed intake valve closure, for example, to make use of any flow momentum, okay? So part of those two things, right? Not having any valve overlap and not having a late intake valve closure is due to the fact that this is a slow speed diesel engine. I think the rated speed on this engine is maybe 1500 RPM. And so, much, much slower than your typical high-speed performance engines. It's designed to produce torque, and so it's not quite so important that it operate at very high speeds to also give very high power. And so it doesn't need, or it would be almost silly to have, for example, a delayed intake valve closure, because you would certainly lose mass from the cylinder as the piston moves toward top dead center during compression if the intake valve were still open based on the speed of the engine. And so that's a typical characteristic that you'll see with low speed engines. They have valve timings that are very, very close to piston top dead center and bottom dead center. You don't see that valve overlap or the delayed intake valve closure or the early exhaust valve opening, right? So that's the other thing, is that when we go into the combustion and expansion stroke, you'll notice that the exhaust valve pretty much opens right when the piston hits bottom dead center. In other words, there isn't any early exhaust valve opening to try to make use of a very quick discharge and blow down and get that cylinder evacuated as quickly as possible in preparation for the next cycle. The engine's just operating too slow to make use of any of those flow dynamic effects that we would typically see. Okay, so that's pretty much everything that I wanted to talk about with this engine. Let me now start to take you through some of the various parts that are on the part cart. Okay, so one of the parts that we would have talked about in class is this piston that you see here. So this is a diesel engine piston from a medium duty diesel engine. So the displacement of the engine might be somewhere between 4 to 5 liters. Or another way to say it is that each cylinder would probably be a little over a liter, maybe 1.2 liters, somewhere between 1 to 1.2 liters for an engine of this size. Okay, so typical, I mean, I don't think that there's anything too surprising when you look at this piston. A couple of interesting features to point out, right? Of course, this is where the wrist pin goes, the connecting rod goes into the bottom. In fact, actually, I have the connecting rod for this engine, so I can show you that. So this is the connecting rod for the engine. So this part here, of course, is where it connects to the connecting rod. And then this part here is where it slips into the piston, and then you use a wrist pin with associated clips to hold the wrist pin in place, and that's basically how the piston mounts itself to the connecting rod. Okay, so I'll talk about the connecting rod more in just a moment, but just to kind of return to some features about the piston itself, you'll notice again that given that this is a diesel piston, you see this this bowl pattern that you have inside the crown of the piston. So again, we call that the piston bowl, and this is very, very common design feature for diesel engines. This particular diesel engine would have up to 6 fuel injection sprays, and so there'd be a radial pattern where the fuel would be injected at an angle that's roughly about that, so that the fuel hits this outer edge of the bowl, and this bowl allows that fuel, that injected fuel, to then mix with the air and create a suitable mixture for proper combustion. And of course, you've got your piston rings that then hold or that create the seal for you between your piston and your cylinder liner. Okay, and I'll talk about the cylinder liner here in just a moment. But returning to the connecting rod, one of the things that I always like to point out about the connecting rod is actually on the back end, or on the big end that you see here. So if you look real closely, you see that line right there. And so that's, of course, where the bottom end of the big end of the connecting rod is separated from the connecting rod itself. So the way that you would install this in an engine is you would have to remove these 2 bolts here, right? And then this whole piece comes off. You sit it over the corresponding bearing in the crankshaft, and then you bolt these back down. But the reason why I like to point this out is because if you look real closely at that line that separates these 2 pieces from each other, and you can see a similar thing down here. It's pretty rusty, so it's a bit difficult to see it nowadays. But if you look real closely, you'll notice that that line is not perfectly straight. It's a bit jagged. And the way that they do this during the manufacturing operation is they actually they purposefully fracture this piece here so that you have a fracture break, as opposed to cutting it right with a tool to actually cut it. And so it's purposefully cracked and fractured, and that actually makes this connection, when you reconnect it, it makes it a much stronger fit. So you have to when you reassemble this, you have to be careful that you're reassembling it the right way, because it has to be mated in the right orientation in order to fit properly. So as I mentioned, the piston and the connecting rod that we were just looking at go inside a cylinder liner. And so this is actually the cylinder liner that would go inside the engine. So this is what is called a wet liner. And the reason why it's called a wet liner is this actually sits inside the engine block. So the engine block would be surrounding this liner, and then you flow coolant along and all around the cylinder liner, and that coolant helps to keep the engine at a proper temperature. And so you'll have a gasket down here that creates a bottom seal for you. You'll have a gasket up here that creates a top seal for you. And then this basically just slides right in, and the cylinder head, of course, compresses the liner down into the block and holds it in place. So the cylinder head would sit right on top of this unit, on top of this liner, all the liners in the block, and basically hold the liner in place, okay? Now, right now, I don't have it such that the piston is inside the liner. And that's usually so that I can point out also another interesting feature here. If you look inside that liner closely, again, it's a little bit rusty, so it's not all that easy to see. But what I'm hoping that you'll see is you'll see some scoring lines that are kind of in a crisscross pattern, right? In other words, you'll see some scoring lines that are going in this direction, and you'll see other scoring lines that are going in this direction, right? You can maybe just see that just a little bit there. So those scoring lines are basically scuff marks that they purposefully use to create a certain surface finish on the inside of the liner to help with oil with oil regulation, right? So or oil control, I should say, inside the liner. So there's a piston inside this liner, and it's reciprocating back and forth inside this liner. So you have to provide some kind of lubrication. So very often there'll be some means by which oil is the oil is sprayed into the bottom of the liner. So the piston would be sitting down here, reciprocating back and forth. And so oil is generally sprayed into this liner to help lubricate that surface, that metal to metal surface between the piston ring and the liner. Well, if you didn't have those scoring marks on the liner, you could have a situation where either oil collects and builds up on the liner, and then that creates gumming issues, or it might flow back into the drain pan down below too easily, which then, of course, robs the liner of the proper lubrication that it needs in order to keep it lubricated. So they have those scoring marks in there to help control the flow of oil along the cylinder liner. Okay, I'm going to put the piston inside the liner and connect or hold the connecting rod there so that you can see what that looks like. Okay, so it always takes a little bit of time, but we eventually get it in there. Ordinarily, there's a special tool that you use to clamp around the piston rings so that you can just slide the piston into the liner a little more easily. Of course, I don't have that tool, so I have to do it the, junkyard mechanic type way, but we get it in there one way or the other. And so now you can see what the piston looks like inside the liner. And if I just kind of slide it back and forth a bit, it's easier to pull on it than it is to push on it. But this is, with the piston at top dead center. And then if I pull on the piston, then you can see, of course, as the piston slides back inside the liner, okay? So on the other side, this is where the connecting rod would go. Don't have the connecting rod connected, but basically it would more or less look like this when it's all assembled, right? With the piston inside the liner, connecting rod, then connecting to the crankshaft down here at the bottom, okay? Okay, so a couple of other parts that I talk about in class. The other really neat thing that we have is the turbocharger. And so this is what we have down here. This is the turbocharger that, again, another student project had worked on for me where oops, you can't see it, sorry. I guess you can't really see it yet either. So let's get this set up a little better. Actually, I might just have to hold the camera for this one and walk around, sorry. Anyway, yeah, so this is the turbocharger. You know what, I'm gonna put this back down below, 1 second. Okay, so this is our turbocharger, and again, this was cut into by a student group. Turbochargers don't normally have sides missing from them like you have here, but the basic construction is, you can get a sense of the basic construction. The first thing to point out is the turbine side. So a turbocharger has a turbine side. So this is what's where the exhaust gas is driving a turbine wheel. So you can see the turbine wheel right here, okay? And basically what happens is the exhaust gases flow in from the exhaust manifold into this portion here. The exhaust gases then go through what we call a turbine scroll, which basically directs the energy of the exhaust gases so that they hit this impeller and cause the impeller to spin, okay? So that turbine wheel, and then the exhaust gases flow out this larger diameter here out to the exhaust pipe. So as the exhaust gases flow through, they cause the turbine wheel to spin. As the turbine wheel is spinning, that causes the compressor scroll to spin. So I'm gonna use my finger to rotate the turbine wheel, and then of course you can see that the compressor scroll is also spinning. So what the compressor side does, so this is the compressor side of the turbocharger, it, as the turbine is spinning by the exhaust energy, causes the compressor scroll to spin. That basically acts as an air pump where it draws air in, so the airflow comes into this large portion here. The air gets sucked in. It then gets pressurized or compressed by the compressor scroll. And then you can see this is a portion of the compressor scroll here. The compressor scroll basically forces, or the compressor wheel, I'm sorry, the compressor wheel basically pressurizes the air into the scroll area and then eventually pressurizes and pumps the air out the compressor outtake or the outflow, which then goes usually through an intercooler, so that because you've pressurized the air, you've increased the temperature of the air through that pressurization, you then pass it through an intercooler, which then cools the air, maintains the high pressure, cools the air, thereby increasing the density of the air so that you have higher density of air going into your cylinder, right? Of course, a turbocharger, the whole point of a turbocharger is to increase the power density of an engine. A lot of times people think that it's designed to increase efficiency, which you can gain efficiency benefits from a turbocharger, but the primary purpose of a turbocharger is to increase your power density. In other words, you're trying to use your compressor to pressurize your cylinders with as much air as you can so that you can generate higher amounts of torque. They're usually used on diesel engines because diesel engines operate lean, so they have less fuel, makes them more efficient, but it decreases their power density. The less fuel you have in the cylinder, the less energy you have available to give you high torque or high power. And so by pressurizing your cylinder with more air, you can then inject more fuel and give you a higher power density or power per unit displacement. Okay, so that's the primary purpose of a turbocharger. Now this particular turbocharger is what is called a variable geometry turbocharger. And what's neat about this is that it allows you, so this ring, which is when we cut into the side of the turbine scroll, we lost the functionality of this ring, but it basically would rotate this set of rings here. Sorry, you can't see that. So this set of rings here basically controls a set of vanes which direct the exhaust energy to be, to either hit the turbine scroll more or less directly, okay? And so the reason why a variable geometry turbocharger is a useful device is that if you didn't have those nozzles or those vanes that were changing the way that the exhaust gases hit your turbine scroll, you would have what is called a fixed wheel turbocharger or a fixed geometry turbocharger, in which case these vanes aren't there and the exhaust gases are just hitting your vanes however they're going to hit them. And so you can change the efficiency of how well those exhaust gases target that turbine wheel and match the speed of your turbine to the compressor speed to change how well the compressor is pressurizing your cylinder at a given operating condition. Okay, so kind of in a general way, it allows you to change the efficiency of the turbocharger, how efficiently it's using that exhaust energy to pressurize air on the intake side. In a more practical sense, variable geometry turbochargers are an advancement to what some of you may know as a wastegate turbo. And so wastegate turbos and now variable geometry turbochargers, they can be used to reduce turbo lag. So turbo lag is a common affliction of turbochargers where if the engine is at a low operating mode, say at low load, low torque, low speed, imagine a vehicle sitting at a stoplight, so the engine is idling, the turbine speed is going to be relatively low, so the pressurization through the compressor wheel is going to be relatively low. All of a sudden the light turns green, person steps on the accelerator pedal and wants to accelerate quickly, and so by stepping on the accelerator pedal, you dump a large amount of fuel into the cylinder, but you don't have the amount of air in the cylinder that you need to be able to support high amounts of power. You have to wait for the turbine speed to accelerate or to spin up before you can start dumping more fuel into the cylinder to get more power based on how much pressurization the compressor side is supplying the cylinder with air. Okay. In other words, to say it more simply, the turbocharger is getting its energy from the exhaust gases, and if you're at an idle condition, you have relatively low exhaust energy. So if you want to accelerate quickly, you have to build up that exhaust energy before you can start having high power density in your cylinders with the pressurization of the air. Okay, they call that turbo lag. And if you have a wastegate turbo, what you do is you design a artificially small turbine wheel so that it accelerates quickly, but then when it gets to high speed, you don't want it to overspeed because that'll damage your turbocharger. So then you use a wastegate to basically dump that energy and maintain a safe operating speed for the turbine. Or you can use what is now the advanced technology, the variable geometry turbocharger, and use this ring, which is connected to an actuator that is controlled by the engine controller, to reorient your vanes differently so that you change the way that the exhaust gases are targeting that turbine wheel and thereby increase or decrease the efficiency of the exhaust energy to change the turbine speed and increase the rate at which you can pressurize your cylinders during an acceleration event, for example. Okay, so long description for really cool technology, but that's basically how it primarily works. Okay, the last thing that I want to show you, which is something that I always love to point out to students and guests of the lab, which is basically this mold that you see here, this blue mold. What this is actually a mold of the clearance volume inside a large 9-liter single-cylinder natural gas engine. Okay. We had to determine, so we were doing modeling of this engine. We have this engine in the lab. We were doing modeling of this engine. And one of the critical things that you need to know in order to properly model an engine is its clearance volume. That is the volume in the cylinder when the piston is at top dead center. Well, there's lots of different ways that you can determine clearance volume, but ordinarily, if you are using or studying, say, a small automotive engine, one of the very common ways that you do this is you fill your cylinder with oil when the piston is at top dead center. You very carefully measure the oil as you meter it into the cylinder when the piston's at top dead center. And however much oil, the volume of oil that you add to that clearance volume space is your clearance volume. Well, this is a horizontally situated engine, plus it's a 9-liter engine, and so you can see this is the clearance volume, so you can see that it's a relatively large volume. It wasn't practical for us to get an accurate measurement of that by using the oil displacement method. So what we did instead is we positioned the engine such that the piston was in its outbound position. Okay, so this portion here is the cylinder head, and this would be basically a negative relief of the piston, with the shape of the piston. Okay, and so the cylinder is oriented horizontally, so we positioned the piston so that it was in its outbound most position, and then we filled the clearance volume with liquid silicon, which would harden after about 24 hours. And so we filled it with the liquid silicon, let it harden, pulled the cylinder head off, and then pulled the mold out. And then you might ask, well, how did you determine the volume of this? Well, that was pretty easy. We just took a large bucket and we made markings on it and filled it with water up to a certain mark. And then we dropped this in the bucket to see what the displacement of the volume was, the displacement of the water. And of course, that displacement then corresponded to the volume of this mold. And that's what told us what our clearance volume was, okay? So there's a few features on here that are kind of interesting to point out. So this comes from a two-stroke engine. And remember, this is the negative of the piston, right? So there's basically, for lack of a better way of describing it, a groove that's cut into this portion of the piston. And then you have kind of this angled elevation, this change in elevation of the piston on this side. Okay, so it's a two-stroke engine. So the way that this is designed to function is this is the exhaust side of the piston. And so when the piston is moving down, it first uncovers the ports. And so you have this portion here that is essentially designed to uncover those ports and allow that blowdown to occur sooner than on the intake side. And then once you do start to uncover the intake ports on this side of the piston, it's a gradual uncovering of the intake ports. And you'll notice that, again, this is a negative relief. So this is basically angling the air up into the cylinder so that when the air begins to rush in, it's being pushed up into the top portion or the outbound portion of the cylinder. And that basically creates almost like a U-type flowing pattern where the gases would rush into the cylinder and then essentially scavenge or push the exhaust gases out the exhaust port on the other side of the cylinder. So that's the reason why the piston is designed this way. And you can see what the shape of the cylinder head looks like. It's basically a hemispherical design that helps support that scavenging flow inside the cylinder. You'll also notice what looks like two, if you look real closely, it looks like those are two bolts that are sticking out of the top of the mold. Well, remember, this is a negative relief, so those are actually bolt holes in the face of the piston. And so those are basically removal screws. The way that you would remove this piston from the engine is, of course, you would disconnect the connecting rod on the other side of this face of the piston, and then you would screw rods into these two holes, right? These two screw holes, and that would allow you to then pull the piston out of the cylinder. Okay, so those are purposefully designed into the piston head so that you can remove the piston during maintenance or repair or what have you. And again, this is the cylinder head side, right? So these are the features in the cylinder head. And so this is basically you have a spark plug port, which is this knob that you see down here. And then this is an air start port that you would use compressed air to start the engine. And this is basically just a knob in the face of the piston that just creates some additional volume there. Doesn't really serve too much functionality. We actually use it now for injecting gas directly in. It's a natural gas engine for directing gas directly into the cylinder, and so this is where our direct injection system sits. Okay, so anyway, pretty cool. Again, that was a student that came up with that idea to measure the displacement that way, and I always thought that was really cool. So this is always one of the things that I like to feature when talking about the parts. Hope you enjoyed the video, and if you have any questions, feel free to email me and we can talk about it. Have a great day.